Okay. Good afternoon, gang. It looks like folks are still trickling in. I did just post that link a second ago, so I think that will take just a minute for people to start actually arriving. We have made it through the portion of the class on logs and exponentials, which means we're pretty much done with that kind of categorical study of different function types. We looked at polynomials and power functions, rational functions, logs and exponentials, which are the building blocks for the majority of the functions you'll deal with in calculus. There is another major topic that we need to confront before the end of the semester, really two other major topics of import. So as people trickle in, I will switch over to the .cam here and talk to you guys a little bit about these remaining major topics. The first one we're going to begin today. So this is MAC1140, section 004. Today is a lecture, and the date is 11/18/2020. Today, we're going to begin our study of systems with a strong emphasis on linear systems. Now, if it was up to me, before the calc sequence, you guys would all have to take an entire class on this stuff. Linear algebra, which is what we're doing a little preview of, this field of studying systems, specifically linear systems, is an entire field of mathematics. I have two books right here on these called linear algebra books. And it is sort of the most important algebraic structure besides the real numbers themselves for calculus. Now, it's not a whole course. It's just one little part of this class where we're supposed to teach you everything you need for calculus. And the good news is you won't need any of this stuff until you get to Calc 3. But if you're going to be any sort of engineer, any sort of scientist, any sort of computer programmer, then linear algebra is going to be your bread and butter. So I think it's a terrible disservice to the topic that we don't get more time with it. This is where you're going to learn about matrices and determinants. You're going to see your first little bits of what's called abstract algebra, where you study algebraic structures besides the real numbers. It's really beautiful stuff. So I just want to get into it. The other major topic that we need to confront before the end of the class is sequences and series. Sequences and series are very, very important. There's also the topic of conic sections, and I'll be giving you a little Thanksgiving break project to play around with conics, but we're not going to make conics a huge part of the course because there really just isn't time. So today we start our study of systems. If you look in your syllabus, you'll see we're about on track. We're about a week behind as we have been through the rest of the semester, and that's okay. Study is the word after begin there. Begin study of systems. So this is where we are. We just finished exam 3. We're going to start talking about systems of equations, matrices, and row operations. That will be the main topic this week. Now, unfortunately, we're a little short on time here as well. So I just want to dive in. Let's get moving. Systems of equations. Now these are addressed in college algebra. They're also addressed in 1033 in most high school classes, so I'm going to move somewhat quickly. A system of equations is a collection of equations meant to be solved simultaneously. Meaning at the same time. Their solutions, the solutions to systems, are points. The notation, what do these things look like? We usually put a curly brace over here on the left, and then there will be one equation, and then beneath that there will be another equation, and then, you know, so on. So for example, 2x plus y equals 0 and x minus y equals 1 is a system of two equations with two variables each. We call this a 2 by 2 system. Two equations, that's the first two. Two variables, that's the second two. Since this is a linear system, there's more than one way to solve it. I'll tell you what I mean by linear system in just a second. But hopefully you guys remember the two methods that you've learned in algebra classes past, substitution and elimination. In this class, I'm not going to fuck with substitution at all. We do everything by elimination, all right? Unless you're dealing with a nonlinear system. So the best way to solve this would be by elimination. Elimination is where you combine the two equations somehow so that one of the variables or more go away. So here, if you add equation 1 to equation 2, we get, just imagine you've got a little bar here and you add these up. 2x plus y equals 0, and then x minus y equals 1. If I add these up, then 2x plus x is 3x, plus y minus y is plus 0, and 0 plus 1 is 1. So you just get 3x equals 1, which means x is 1/3. But this isn't the whole solution. Remember, the solution here should be a point. It should be an ordered pair. To get the other point, or the other number in the ordered pair, sorry, you then take this and substitute it back into one of the originals, either one. It's called back substitution. We back substitute the value x equals 1/3 into either original to get y. You'll get the same y out no matter which one you back substitute into. So let's back sub into the second one. X minus y equals 1. If I plug in 1/3 for x, that will become 1/3 minus y equals 1. And then if I subtract 1/3 from both sides, that will become negative y equals 1 minus 1/3 is 2/3. And then if I multiply both sides by -1, I get y equals 2/3. So our solution is the ordered pair 1/3, comma 2/3. It's possible that we would have more than two equations. It's possible that each of the equations would have more than two variables. You could, in other words, have a 3x3 system, or a 3x7 system, or a 10x4 system. All of these are possible. Before I start looking at larger systems, I just want to see how to interpret these guys geometrically, and I'm sure you've seen this before. First, any questions on this elimination process we used to solve here? I see there's something in the chat, yeah. How did I get 2/3? So I have this x minus y equals 1. That was one of the original equations. And I know that x is 1/3 from this work. So I plug in 1/3 for x here. So I have 1/3 minus y equals 1. Then I subtract 1/3 from both sides. 1 minus 1/3 is 2/3. Oh yeah, this would become negative when we divide both sides by -1. Yeah, so this should be a negative 2/3. Thank you. Yeah, definitely a negative 2/3. So our last step here is to get rid of the negative on the left, multiplying both sides or dividing both sides by -1, giving us this. Yeah. So it's a negative 2/3. Thank you. Any other questions on this elimination process? What we did here to get rid of the y? Okay, so let's talk about the geometric interpretation. If I take those two equations, the first one is 2x plus y equals 0. Which is the same as saying y equals -2x. And the second equation, which was x minus y equals 1, which is the same as saying y equals x minus 1. Let's see, add y, subtract 1, yeah, x minus 1, and you graph these. Y equals 2x is a straight line going through the origin with a slope of 2. That would look something like this. Oh shit, no, it's supposed to be -2x. Damn, all right, sorry. Getting ahead of myself. So y equals -2x is a straight line through the origin with slope -2, looking like this. That's equation 1. And y equals x minus 1 is looking like this. That's a line of slope 1 with y-intercept 1. So here's 1 and here is -1. And this point right here, this point is the solution. The solution to the system is the point where these lines intersect. And that point just happened to be 1/3, comma, -2/3. And from the graph, I could have guessed that that point is 1/3, comma, -2/3, but I also could have guessed lots of other things that look about right. Yeah, like we can say that the x value is between 0 and 1, but I would have no way of saying that it's exactly 1/3 without doing the work. And I could have guessed that the y value is like, you know, negative something, -1/2 or negative, you know, 0.7, but I wouldn't have known that it's exactly -2/3. But it is important to know that the geometric interpretation of the system is the graph of these two equations, the graph of these two lines, and that the solution to the system is the place where all of those things intersect. Questions on this interpretation or on that elimination process? Okay. So one more definition here. A system of equations is called linear if all the equations in the system are linear in all of their variables. This means that variables are only appearing upstairs, never in a denominator, only to the power of 1, and never inside, like an exponential or some other nonlinear function. Okay, so if the variables only show up to the power of 1 in the numerator and never inside a nonlinear function like 2 to the x or something like that, square root of x, then the system you're dealing with is linear. If any of those conditions are not satisfied, then the system you're dealing with is not linear. Only to the power of 1. So only appearing upstairs, only to the power of 1. So I'll look at some examples. All right. Is this first system a linear system? Are both of the equations there linear One way to think of this, if there's only two variables, is to ask, are both of the graphs straight lines? And the answer here is yes. This first guy is linear. Every time a variable shows up, it's raised to the power 1. The variables are never underneath a square root or in any sort of nonlinear function. Even though there's a square root of 2 here, this equation is still a linear equation. You could put it in the form y equals mx plus b, where m and b are constants. They're weird constants, but they're still just constants. And again, the way we think of this is like, where are the variables? Okay, well, the variables are here. They're each showing up in the numerator, right? Not in the bottom of any fraction. They're each being raised to the power of 1, and the variables themselves are not inside any sort of weird functions. This second guy is not linear. Because of the squares here. X and y here are being raised to the power of 2, and that breaks this rule. The second equation is linear, but the first equation is not. And the third system here is also nonlinear. Both equations here. Because here the x is inside the natural log, which is definitely not a linear function. And here the y is inside e to the y, which is definitely not a linear function. The system at the bottom is a little bit tough. The system in the middle is still manageable. The way we solve nonlinear systems, like the second and third system here, is with substitution, a technique that most of you probably relied on to solve even linear systems in past classes. We try to get away from substitution because elimination is the method that generalizes better. But if we have to use substitution, then we will. And nonlinear systems are cases where we have to use substitution. So I'm going to show you just one example of solving a nonlinear system. We'll do it by substitution. But then we're going to return to our focus on linear systems. First, any questions on what makes a system linear or nonlinear? Or why any of these three examples fall into the category they do? Okay, just for fun, let's go ahead and solve this second system. So we're going to solve the nonlinear system x squared plus y squared equals 9 and x minus y equals 0. Here we have to use substitution because there's no way to add these or subtract these or combine them to make a variable disappear. What we mean when we say substitution is you solve one of the equations for one of the variables. Then you plug that expression into the other equation. So I'll solve equation 2 for x. X minus y equals 0. That's the same as saying x equals y. Now I'll plug that into the equation 1. I'm substituting. When I plug x equals y into equation 1, that's the substitution step. So if x is y, then x squared plus y squared equals 9 is the same as saying y squared plus y squared equals 9. And y squared plus y squared, you see the goal here, just like the other method, elimination, is to get to a place where you've got one equation and one variable. So this is the same as saying 2y squared equals 9, which is the same as saying y squared equals 9 halves. And now we can take square roots. We find that y has to be plus or minus the square root of 9 halves, which is plus or minus 3 over the square root of 2, because the square root of 9 is 3. If you draw the picture here, the graph of the first equation is a circle with radius 3 centered at the origin. That's the graph of equation 1. And the graph of equation 2, that's the same as y equals x. That's the line through the origin with slope 1. So your solutions, there's 2 of them, are this point and this point. So the 2 solutions, we take this and back substitute here. We have x minus 3 over the square root of 2 equals 0, which means x is equal to 3 over the square root of 2. So one solution is 3 over root 2, comma, 3 over root 2. And x minus negative 3 over root 2 equals 0, which would mean x is negative 3 over root 2. So that gives me the solution negative 3 over root 2, comma, negative 3 over root 2. And those are my 2 solutions. 3 over root 2, comma, 3 over root 2, and negative 3 over root 2, comma, negative 3 over root 2. So this here is 3 over root 2, comma, 3 over root 2. And this here is negative 3 over root 2, comma, negative 3 over root 2. Again, this should be refresher from college algebra. But I know with COVID and everything online, I have no idea if your college algebra class got to this point or not. They should have, but I trust that not all of them have. So that's the quick and dirty introduction to the 2 methods we use to solve systems. Elimination, which we use for all linear systems, and substitution, which we use in nonlinear systems. This was a nonlinear system, so we solved it using substitution, which is where you solve one of the equations for one of the variables, then substitute that into the other equation. That'll let you find some numerical solutions, which you can then back substitute into the other equation to find the other value of the variable. So if the y's are 3 over root 2 and negative 3 over root 2, then these are the corresponding x's, and these are the solutions, these 2 points. In the picture here, like in the linear case, your solutions are the places where these 2 graphs intersect. All right, give me some sign that we're still alive, that we're following along, or let me know if you have questions. Okay, doesn't sound like there are questions. So I want to talk about how many solutions a linear system can have. Nonlinear systems can have 0, 1, 2, really any number of solutions. You can imagine that if I picked a different line, right, if I use the same circle, x squared plus y squared equals 9, but a different line, a line that moved all the way down here, then this system would have had no solutions. I could have moved this so that the line just barely kisses the circle once here, and then we would have one solution. As it is, we have 2 solutions. And if I use some other squiggly thing rather than a circle, we could have had 3 or 4 or more solutions. So nonlinear systems, anything is possible. Linear systems, however, things are much more restrictive. It's possible to have a single solution, one place where those 2 lines touch, it's possible to have no solutions. Maybe my 2 lines are parallel. And it's also possible to have infinitely many solutions. Maybe my 2 lines are really the same line. So for a linear system, there's only 3 possibilities. You have a unique solution. One solution, another word for this is unique. No solutions, or infinitely many solutions. the case where there's one solution, a unique solution, we saw an example of that. That was the first example we did. I'd like to show you an example of each of these. And then I want to start talking about larger systems. I do want to take a second here, though, to regroup because I haven't heard much from you guys. You've been quiet, and this is new material. So I just want to know, please tell me how you're feeling. You give me a thumbs up react if this is easy, boring, you remember it all. You can ask me to pause for a minute just so you can keep writing. You can ask specific questions about the examples that we've done. Please just give me some sort of feedback. How are we feeling? Okay. Okay, cool. Feeling good. All right. I'm glad to hear that. So let us then look at an example of systems with no solutions, infinitely many solutions, and then larger systems. And that's about all we'll have time for today. A system with no solution. Oh, let me change this, sorry. All right. So this I claim is a system with no solutions. You could graph the two lines and verify that they never touch just from the picture. But a mathematician likes to be a little bit more careful. So let's see what happens if we try to use elimination. If I add these two equations together, the x's, the y's, nothing goes away. So instead, let's multiply through equation 1 by 3. That will change how the system looks, but it won't change what the system is. It won't change the solutions. Remember, if you multiply on both sides of an equation by a constant, it doesn't actually change the equation. That's one of the things we do when we're solving equations, is multiply both sides by 5 or divide both sides by 2. Here, I will multiply both sides of equation 1 by 3. 3 times 2x is 6x minus 3 times 3y is 9y. And 3 times 1 is 3. And then down here I have 6x minus 9y equals 5, unchanged. Next, I can multiply through equation 2 by -1. These, by the way, are called row operations. When I multiply through a row, i.e. an equation, by a constant, I'm doing an operation to the system. I'm fucking with the system in some way. The sort of things you can do to a system without changing the solution is multiply through any row by a non-zero constant, and you can add two rows to each other. So my next row operation here is to multiply through the second equation by -1. So equation 1 stays the same. Now I multiply through equation 2 by -1. That will give me -6x plus 9y equals -5. And my next row operation is going to be to add equation 1 to equation 2. 6x plus negative 6x. I'll write it out like I did the first time. So I want to add these bad boys up. 6x plus negative 6x, that's 0. 0x if we want to be careful. Negative 9y plus positive 9y, well, that's 0y. And 3 plus negative 5 is negative 2. Now, I don't know about you, but 0x plus 0y, that's 0. So this says 0 equals negative 2. Is that shit possible? Is 0 ever equal to negative 2? No. Or equivalently, are there any numbers x and y you can plug in here to make this a true statement? No. This is called a contradiction. Contradiction is just a statement which is always false. I say always, meaning like no matter what you plug in for x and y. There's nothing you can plug in for x and y to make this true. So it is always false. Which means that there must have been a bad assumption along the way. Have you guys ever heard of Ayn Rand? She's a decent writer and a decent philosopher from the early 20th century. Cool. Had to flee Russia during the Bolshevik Revolution because her parents were wealthy merchants. And she did a lot of writing in America where she escaped the Red Revolution. And she used to famously say, if you arrive at A and not A, then you need to re-examine your premise. You have a false assumption somewhere. So here we have arrived at 0 equals negative 2, which is a contradiction of the sort that Ayn Rand was talking about, which means that somewhere we made a bad assumption. Now, each of these steps is fine. These are normal row operations. There's nothing wrong with them. The problem we made is we tried to solve the thing. We're assuming that a solution exists. So since we arrive at the conclusion, or the contradiction, sorry, under the assumption that a solution exists, there must be no solution. Should say, examine your premise. The premise here is that a solution exists. You must examine that. Oh shit, that must be wrong. The two lines here look like this. The first one has a slope of 2/3 and a y-intercept of 1/3. So here's the graph of equation 1. And the second one has the same slope, but a y-intercept of 5/9, which is bigger. These lines are parallel. They never touch. This is equation 1. This is equation 2. The lines are parallel and separate, so they never touch. Which again would tell us no solution. But this is an algebra class, right? You guys are in this class to learn algebra. Here is the algebra process for discovering that there is no solution. You try to solve, and then you reach a contradiction. So if you get something like 0 equals 2, or 0 equals 1, or 5 equals pi, that's a contradiction. If you do nothing but legal algebra steps and you arrive at a contradiction, then the system you're working with has no solution. Not too bad, right? Questions on this? Either the algebra or the picture or the concepts? Check and make sure my chat is working here. Okay, moving on. How do you know if you have a system with infinitely many solutions? How do you know? And also, how do you find them? Just because there are infinitely many solutions doesn't mean every ordered pair is a solution. For example, there are infinitely many even numbers. That doesn't mean every number is even. There are infinitely many prime numbers. That doesn't mean every number is prime. Just because there are infinitely many solutions doesn't mean you don't have anything to do. It just means that the system fits into that category. So here's an example of a system like that. Again, we should try to solve using elimination. We always use elimination for linear systems. Just like in the previous guy, I can't just add these two and have a variable go away. So first I need to do something. And my first thing to do here, if I want to make one of these variables go away, I'll multiply through equation 1, the first equation, by -3. That's my first row operation. I'm going to multiply everything in this first row by -3. 2x times -3 is -6x. Negative y times -3 is plus 3y. And 1 times -3 is -3. And the second equation stays the same. I'm not doing anything to it. Now I can add the two rows. So -6x, you can see what's going to happen. Plus 3y equals -3. And 6x minus 3y equals +3. If you add these up, -6x plus 6x is 0x. -3y plus 3y is 0y. And -3 plus 3 is 0. This says 0 equals 0, which is the opposite of a contradiction. A contradiction is a statement that's always false. Most of the things you encounter are propositions, which are true or false depending on the values of the variables. This is called a tautology. Which is a statement which is always true. So if through legal algebra steps you arrive at a tautology, then you know your system has infinitely many solutions. One of the things that you absolutely must learn how to do in this class that not everybody requires in college algebra, you've got to be able to tell me what the solutions are. You can't just tell me that there's infinitely many of them. If we look at the picture here, this is the same as y equals 2x minus 1. So the picture looks like this. Both equation 1 and equation 2 have this same graph. Right? So one solution is the point 0, comma, -1. If you plug in 0 for x and -1 for y, this is true. You get 0 minus -1 equals 1. And if you plug in 0 for x and -1 for y, here you get 0x minus 3 times -1 equals 3, which is true. Both of these are true. But how can we write all the solutions? There's infinitely many of them. Well, shit, my hand's going to get tired, isn't it? Any point on that line any point on the line graphed above will solve this system. So the set of all solutions is the set x comma y such that x comma y is on the line. But that's a very cumbersome way to write that set. A nicer way to write that set is by solving this 2x minus y equals 1 for y. That's the same as saying 2x minus 1 equals y. So this would be the set x comma 2x minus 1, where x is any real number. This would be your solution set. Let's review the set builder notation just for a minute to make sure everybody's comfy with what I mean by this. This is the kind of first challenging new thing we've talked about today. This curly brace and curly brace here, this means the set containing. So this is the set containing all the ordered pairs, right? This is an ordered pair, parentheses x comma 2x minus 1. This is the set containing all the ordered pairs of the form x comma 2x minus 1, such that this vertical bar is such that x is any real number. Is this making sense? You all remember what this set builder notation is? You say the set of all these objects subject to these restrictions. So this is the set of all ordered pairs x comma 2x minus 1, subject to the restriction that x is any real number. How did I get the 2x minus 1 here? I solved the equation, doesn't matter which one, either one, solve the equation for y. This is only what you do if you have infinitely many solutions. You wouldn't do this in any of the other cases. But when you have infinitely many solutions, you need some way to write them all down. I can't just give you this one solution, and I can't just tell you that there are infinitely many solutions. I need some way of saying, here's the box that has all of the infinitely many solutions. All right, well, here it is. Here's my cardboard box with all the ordered pairs that solve this system. All right. So you guys have now seen all the three possibilities for a linear system. It can have a unique solution, like the very first one we looked at. No solutions, like the one we looked at a second ago, which you learn when your solving process, your elimination process, leads to a contradiction. And then you can have a system with infinitely many solutions. You know that you're in that case when your elimination process leads to a tautology. On exam 3, I will be testing your ability to do this. Not just this, but specifically using elimination. So if you didn't really learn elimination in your last class, you kind of snuck by using substitution or guessing and checking or whatever, now it's time to actually learn elimination. There's no way around it. Gotta learn it. Questions on any of these examples so far? Okay. One of the things we're going to do is look at bigger systems. So in general, an M by N system of linear equations is a system with M equations, each containing the same N variables. So for example, x plus 2y minus z equals 5, 3x plus 0y plus 2z equals 0, and 2x plus y minus 3z equals 2 would be a 3 by 3 system. Three equations, each containing the same three variables. Here, x, y, and z are the three variables. It turns out that the rule we discovered for 2 by 2s is the same for 3 by 3s, meaning there's either one solution no solutions, or infinitely many solutions. It's not possible to have 2 solutions. It's not possible to have 5 solutions. The reason for this is because of the way planes intersect. So remember, the solution to a 2x2 system is about how lines intersect. They either intersect in one point, they never intersect, or they're the same line. They intersect at infinitely many points. Planes are like flat pieces of paper. If you think about how 3 planes can intersect, you'll realize that the same possibilities exist. Now, these pictures get very hard to draw. So I'm going to ask you to just watch with me here. Here you go. And I'll look for one better picture. Maybe there's one where they're slightly transparent. Yes. And here. All right. What? Whoa, 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 hold the fucking phone. Yeah, you are the last one I wanted to pull. Okay. So how can planes possibly intersect? Well, if you have 3 planes and they're all pointing in different directions, there's like 3 axes you can rotate about. So this blue plane and this red plane and this light green plane, if you look at where all 3 of those intersect, that's this unique point, this one point. That's not the only possibility, though. Let me find something that's a little clearer. Like this. Yeah, this is starting to get a little bit better. So if you look here, here's just two planes intersecting. 2 planes, if they're not the same plane, they'll intersect in a line, like this plane and this plane. If you ask where do they intersect, what points are on both planes, there's this whole line here. And then if you drop in a 3rd plane, that will chop this line down to a single point. Then you'll be in the situation like this, where you've got just one point. But there's lots of possibilities. However, no matter how you think of those possibilities, I just want these pictures. Here we go. There's still only 3 possible solution sets. If you're looking at 3 planes, all 3 could be the same plane. This would mean you have infinitely many solutions. All 3 could be separate parallel planes. This would mean you have no solutions because there's no point that lives on all 3 planes at once. You could have 2 of the planes parallel and then 1/3 plane slicing both, but again, no point that is common to all 3. So all of those would be no solution, right? This is no solution. This is no solution. This is no solution because there's no point that's common to all 3 planes. This guy right here would be infinitely many solutions because every point is common to all 3 planes. This point right here, how many this picture right here, how many solutions would we have in picture 7? How many points are there that are common to all 3 planes? Well, every point along this line is on all 3 planes. So there's infinitely many solutions in picture 7. How many solutions in picture 8? Are there any points that are on all 3 planes? We've got two planes that intersect in a line here, two that intersect in a line here, but those never touch. And then those guys, they intersect over here, but this line doesn't touch either of the other two lines of intersection. So if you think about it, these are all the possibilities, but they all fit into one of those categories: infinitely many solutions, one solution, no solutions. So this first guy, infinitely many solutions. This second guy, infinitely many solutions. Here, the first two planes are the same. And then where this third plane intersects is this line. And there are infinitely many points along this line where those planes intersect. In this picture, there are no solutions. The first two planes are identical, but this third plane is parallel. So there's no point that is on all three planes. This guy, no solutions. Again, two parallel planes. So there's no point that lies on all three. All three planes could be parallel and separate. No point that lies on all three. Here, all three planes intersect each other differently, and there's one point, exactly one point that lives on all three of them. So this is the nice situation where there is a unique solution. Here, if all three meet along a common line, then there's infinitely many. And here, there's no solution because, again, there's no single point that lives on all three planes. So 3x3s, 4x4s, in general, linear systems always still have 0, 1, or infinitely many solutions, no in between. Let's try to classify this guy. What's the size of this system? Is that a 2x2, 3x3? Something else? How many equations do I have? Please show me that you're present. How many equations are there in this system? 3. How many variables does each of those equations have? 2. So this is a 3x2 system. Okay, one more of these. Classify this guy as his size. This is a what by what system. How many equations are there here? Good, yeah, this is a 2x3 system. So, regardless of their size, linear systems always have either 0 solutions, 1 solution, or infinitely many solutions. And these bigger systems, 3x3s, 2x2, 2x3s, 3x5s, whatever, we can solve them by elimination also. So when you're looking at a 3x3, each one of these equations, let me show you something. Desmos can't do this, but Wolfram can. The graph of such a thing, like x plus 2y minus 3z equals 1, is a plane. The graph here is three-dimensional, and it looks like this. Now, I can't move it around, but so when we're looking at a system that has three variables in each equation, we're looking for the intersection of this plane with this plane and this plane. So like we saw in those pictures a moment ago, three planes, this first plane, this second plane, and this third plane, they'll either not touch at all, or they'll all meet in one point, or they'll meet along a line. So they'll have either no solutions, one solution, or infinitely many solutions. A 3x2 system, each one of these equations has a line as their graph, not a plane. So here I'm asking, how could these three lines intersect? Well, just like two lines can either not intersect, intersect at a point, or intersect everywhere, this can have 0, 1, or infinitely many solutions. The first number is the number of equations. Here I have 1, 2, 3 equations. So the first number is 3. The second number is the number of variables. I have x, y, and z. So this guy is a 3x3. It has 3 equations, and each equation has 3 variables. This guy also has 3 equations, 1, 2, 3. But each of those equations only has 2 variables, x and y. So this guy is a 3x2, 3 equations, 2 variables. And this last guy has 2 equations, 1, 2, and each equation has an x, a y, and a z. So this is a 2x3. Regardless of their size, they all fit into one of these categories: no solutions, one solution, or infinitely many solutions. And systems where m is equal to n, same number of equations as the number of variables. These are called square systems. Like 2x2s, 3x3s, 4x4s, and so on. These would all be called square systems. So the top example here, the 3x3, that's a square system. A neat fact is that only square systems are capable of producing a unique solution. If you have more equations than you have variables, then you will have what's called an overdetermined system. If you have more variables than you have equations, you have what's called an underdetermined system. And those correspond to having no solution or infinitely many solutions pretty much all the time. But the nice situation is where you have the same number of variables as you have equations. I'll be posting fresh homework today for you guys. And it's going to be just on solving systems like these by elimination. So we've seen how to solve 2x2s. We've looked at, but not solved, some 3x3s. Let me walk you guys through actually solving a 3x3. Oh, let's see, where are we at? We're out of time, aren't we? Okay, so we're not going to have time to explicitly solve a 3x3 today. Next time, that's where we're going to pick up. Sure. So systems where m and n are equal are called square. Since we're out of time here today, I will come back at this point on Wednesday, right? So you guys had a test on Monday. So next Monday, we're going to start looking at how to solve 3x3 systems. And I'll also introduce matrix algebra. I am going to open up a homework, and I'd like you guys to get started on it. Many of the questions you'll be able to answer just based on what we've done today. But when you start running into the larger systems, 3x3s and so on, I won't expect you to solve them. You're welcome to try. So please take a look at the homework that's going to open up in a little bit, get started on it. But if you get stuck or whatever, that's okay. We'll pick it up here Monday talking about how to solve these bigger systems. From here, we're going to start talking about matrices. Matrices are a nicer way of writing systems. Rather than writing all this gobbledygook, you can just write some numbers in a square or in a rectangle, and then just work with those numbers rather than all the variables and equals and plus and minus. But yeah, that's it. That's where we'll have to leave it for today. So that is all. And I'll get working on grading your exams right away. They'll be available for you by next Monday. All right. I hope you guys have a lovely rest of your day. Please do take a look at that homework. It'll open up later today. And then I will see you on Monday.